All right, we're recording.
Okay. So we're here for the midterm review. So we're here to answer questions. Hopefully you guys watched the pre-recorded video that we posted last week, or earlier this week rather. That's probably the best resource to watch, because we go step by step. And it was back when we were newer TAs and we were closer to this material, I guess, in a sense. But we're here now. So if you have any lingering questions, or if you didn't understand something, that's what we're here for. So I guess we'll open the floor to you guys.
I heard a chat come in. Oh, admit. So Oscar wants to join too. Anybody who comes from outside the ASU email exchange, I have to approve. It was annoying. Anybody have any questions? Anything they want us to touch on? How's the class going? I mean, any questions about the program? Want to be a UGTA? I can send you a flyer in an email.
Yeah, just to clarify, this live session today was intended to answer any lingering questions that weren't covered in our pre-recorded video.
Yeah, we have no material prepared.
Yeah. If you haven't watched that video, then you probably should watch that video. It's a little long, but the benefit is, since it's pre-recorded, is that you can skip ahead to just the problems that you need to work on. I always advise going through the practice exam yourself, and then once you get stuck or have a question, then going to our review session, the pre-recorded one, skipping ahead to the question that you're on, getting the feedback. Or actually, for me in my classes, I actually just watch reviews, without going through the reviews myself, just to see what they have to say about it. So I guess both methods work.
And I actually watch them again to remind myself of concepts. Like when someone asks me a question about discrete time convolution, I have to go rewatch that little section of discrete time convolution to remember how to do it. Yeah. So they are useful.
These guys can unmute themselves, right?
Should be able to.
Okay.
Oh, there's a chat. Hello, Peter. Peter says he is struggling with understanding continuous signals in a discrete time.
So a continuous signal in a discrete time, all that means that if you have a plot or curve of a continuous time signal and you have a sampling rate, you're just going to be taking the whatever amplitude that signal is at those discrete sample periods. Does that answer your question? I have
problem 329 is what he's referring to.
329 of the homework?
Yeah, I think there was a
Let me open that.
Post about that. But.
Oh, I probably need to grab my textbook. See what this problem is even asking for. Okay, 329 is asking In each of the following, we specify Fourier series coefficients of a signal that is periodic with period 8. Determine the signal x of n in each case. So you're given the Fourier series coefficients. That basically is the signal in a indirect way. Determine the signal. So 429D. It looks like the triangle cosine wave, but with the discrete pulses. So, figure 329 in the textbook is referring to.
Yeah. Yeah, it looks like they just expand out the series and then combine them into sines and cosines, and then that's all.
Yeah.
Yeah.
So, yeah, you just start at any arbitrary point on the graph, and you're gonna basically write down the coefficients as a series of sums, a series. You have a period of 8 that's given to you in the problem, so you're gonna write down 8 terms. So let me go ahead and screen share. This program's a little different than the one we used to, so where is the button for it? Am I able to screen share on this, James?
Yeah, it should be able to.
I just
Remember now.
Oh wait, did I do anything?
Well, I'm in the 4 block position now.
If I click my own icon or whatever in the chat or in the people list, it makes
It's
my
down on the bottom. When you bring the mouse all the way down.
Oh, I see it. Okay. Present now.
Yeah.
My entire screen. Screen 1 share. Okay. Hopefully you guys can see my screen now. My mouse is moving around. I'm looking at the homework. So you guys confirm if you can't see it or not. But I wish I could show the picture of the plot. But okay, so the plot is as Peter said, is a triangular looking like a sawtooth wave, but in discrete time. So you have just little spikes that are in the shape of a triangle. Now the problem says that there's period 8, so I'm going to take any consecutive random 8 of these spikes, and I'm going to draw them out as a series. So if you look here, what I'm highlighting, there should be 8 of these. So I see 1, here's the DC one, 2, 3, 4, 5, 6, 7, and 8. So usually when you're choosing what spikes to use, you would want to use the ones that are most convenient for the mathematics, or just to have a good starting point. So I usually start at 0. In this particular problem, it doesn't really matter. So I'm going to start at 0. At 0, if you're looking at the same plot in your own textbooks, I'm going to 0 is the amplitude of 2, and then the next one is the amplitude of 1. The next one is the amplitude of half, and then the next one is the amplitude of a quarter, and then it goes to amplitude of 0, and then you rise back up, and that completes the series of 8. So if 0 is amplitude 2, I gotta see what they're doing here now. Okay, so this line that I've highlighted, they're just writing out the series coefficients in a very generic sense from basically the definition. So they just say, I have my first one, my second one, my third one, so on and so forth, and they're just attaching complex exponentials to them. Now they have the period here as well. These are let me look at the definition real quick. So chapter 3, key concepts. The definition says that a Fourier series coefficient is 1 over n times a coefficient times the complex exponential. The complex exponential is a k and an omega naught. Our omega naught is going to be based off the period of 8. You have to convert it to the angular frequency though. Where is it? So they're saying omega naught is 2 pi over 8.
And 2 pi n over 8. Oh, no.
Yeah, so the 8 is the period.
Yeah.
And then the next line makes it a little bit better. It actually puts in the amplitude, so you can see our first pulse starting at n equals 0 is amplitude 2, and then our second pulse is amplitude 1, then amplitude half, amplitude quarter, amplitude 0, so this term will actually fall out later. Then we rise back up at amplitude, quarter, half, 1, and then the period is over. Now the other step that they took in this line here is that they added the K values. So the K values are basically the index of what coefficient you're looking at. So this one was an index of 1, this one should be an index of 2, index of 3, so on and so forth. So if you multiply the K times the omega naught, if I'm saying that this one is a K equals 1, that means that K equals 1 times 2 pi over 8. 2 pi over 8, you take the 2 and the 8, you reduce it down to 1 over 4, and that's where that comes from. Then over here, it's going to be K equals
2.
0, 1, 2, yeah. So 2 times 2 pi over 8, what does that come out to? Well, 2 times 2 pi, well, that's 4 pi. 4 pi over 8 is going to be, you reduce it down to pi over 2. So that's where that comes from. And you follow that same pattern throughout here. K times omega naught, K times omega naught, K times omega naught, so on and so forth. The next steps after that, says here convert phase to between negative pi and pi to see if they can be combined into sine of cosines. So that's a little mathematical trick just to make these all line up. Because from Euler's formula, just to go back to chapter 1, week 1 material, we have these definitions, or rather identities, using Euler's formula. This is Euler's formula. You have to do some manipulations to get it into these forms for the cosine and the sine. We don't really do that in class, but you can always Google that.
Yeah, there was a homework on the first homework to derive those out. But
needless to say, though, the pattern for these cosines and cosines in terms of complex exponentials is, for cosine, you always have complex exponential with a positive j plus a complex decaying complex exponential, with a negative sign, and then you multiply by a half. For the sine, it's the same thing except for you multiply by an imaginary 1/2, and you have a minus sign. So, anyways, back to the homework problem. We want to get the series of coefficients into a form that we recognize, such as this. In other words, we want our thetas to match. We want a positive theta and a negative theta, and then we'll manipulate it to transform it into the cosine or the sine. So back to the homework. That's what they mean by this step. So the way you actually do that is
they're subtracting 2 pi from what would be the negative exponentials, because they went when they wrote the series, they started at 0 and then went to 8. You could have also started the series at -4 and gone to 4 and skipped this whole step. But that's basically what we're doing.
That's a good point, actually. So at this step, when we, or rather, this step, actually, you could go as far back as, what do we choose for here? Well, the professor chose 0 to 7 for a period of 8. But what Jamie's saying is that you could have done k equals -4 all the way up to, well, 3, I guess. Yeah, -4 up to 3.
Well, -3 up to +3, and then skip. Well, yeah.
Yeah.
-4 would be 0, and +4 would be 0. But.
Well, yeah, you'd have to do -3 to +4, or -4 to +3, actually, because you have to include that that 0 amplitude term as well.
Yeah.
But either way, yeah, you could have done that and then skip this entire step altogether. But it's always useful to know how to do this as well. So as Jamie mentioned, all they're doing is taking these k times omega naught and adding or subtracting 2 pi. And then once you do that, they should start, 2 out of the 8 terms should start lining up with each other and have the same theta, if you will. looking at the definition here, that's what theta would be. Anything that's after the j, basically, the argument of the complex exponential. So, does that answer your question? Or sweet.
Cool. Anybody else have any other questions, homework they're having trouble with, or want us to go over? Or? So, anyway.
You guys want to see a cool little thing I made? I usually show this at the final exam review.
Yeah.
It gives a little sneak peek at the rest of the course and like why we're learning this stuff. And I think it's for the folks that like to get out of take their blinders off and get out of just solving problems, like and you know, they wonder why, you know, people sometimes wonder why we're learning this stuff. This stuff is very widespread, or you know, you'll see it pop up a lot in engineering courses and in engineering work. What just happened? Am I still sharing? Yeah, I'm still screen sharing.
Yeah.
Okay. So anyways, this thing just outlines basically the major topics of the course. So the first week, actually the first 2 weeks, are basically just laying a foundation for like using terminology and being able to understand, you know, reading the equations that we see for the rest of the course. But in general, in a very broad sense, a forest for the trees sense, we learned 4 major topics, and they're used for very specific things. So for week 3, we just started learning Fourier series. After the midterm, we're going to start learning Fourier transforms, Laplace transforms, and Z transforms. Now, you should have seen Laplace transforms in differential equations, and maybe how to. Anyways, you should have seen that before, but we use it again in this course. But we look at it from a different perspective, from a signals and systems perspective. Okay, so anyways, a Fourier series. Why are we learning that? Well, to bring it back to like circuit 1 and circuit 2, and you know, analog and digital circuits in general. The whole point is to analyze a system such as a circuit for us electrical engineers for steady state frequency analysis for a periodic signal in continuous time or time. So in other words, we want to know, what does the system do after it's stabilized, after it's been on for a little while? You know, a little while being a few milliseconds or a couple dozen milliseconds. In other words, this gives us a solution that does not include transients. Transients being when you first apply power to the system, you get a little spike and then settling of currents and blah, blah, blah. Well, Fourier series cannot describe the behavior of the transients. For that, we would need the Laplace transform. But before I get ahead of myself, so the Fourier series is just for signals and systems that are periodic, which really is a whole lot of the stuff we work with in engineering, because we're talking about computers, you know, finite state machines that have clock signals, and the only part that's not periodic would be user input or like sensor inputs, things like that. But like the rest of the system is basically periodic. Now, if we're talking about a system that does not have something that's periodic, it is aperiodic or non-periodic. Then we'd have to use the Fourier transform, which is basically the Fourier series, but it can describe a periodic signal with an infinite period. And that's the mathematical trick that we use to get the Fourier transform from the Fourier series. So again, it describes a steady state frequency analysis, but this time for an aperiodic signal, both in continuous and discrete time. Now later in the course, we get into the Laplace transform. Now the Laplace transform is a even more general case of the Fourier transform. The Fourier transform, and we'll get into this after the midterm. Well, never mind. I won't describe that right now because it's not important. But the Laplace transform describes the entire full or complete description of a signal or system. So this includes both the transients, like when you first turn on the system or when you first disturb a system, things like that, and the steady state. Now the Laplace transform can only handle continuous time. So since we still, as engineers, design and work with systems that are discrete in nature, because computers are discrete machines, to be able to do the same thing in discrete time, we use the Z transform, and that's the whole course. That's what Signals and Systems 1 is about. So I hope you guys appreciate that. I always find it useful to know or understand why we're learning something, so that when I dive into the weeds of a problem, it helps me survive and get to the end of the problem. Gives me a little bit more endurance. Do you guys have any questions about just very general concepts about the course, or what is Euler's identity? I don't know, what is it? Is anything? Another little sneak peek, I guess, to get you excited about the second half of the course is, especially if you're gamers, if you play video games, and you have seen, the graphic settings for anti-aliasing. Well, the second half of the course, we get pretty in depth into what aliasing is from a mathematical standpoint and how it affects systems. I think that's pretty exciting too. I'm not going to describe it here because that's the whole. We're talking. This is a midterm review.
It's a teaser.
Yeah, just a little teaser. All right. Here it says, what are some of the concepts you had trouble with in this course? Things that you came to understand that you wish you have known sooner. Well, that's a good question, actually. So, what I'm about to say, I think, has largely been solved. But in the when Jamie and I first started TAing this class, we saw a few patterns. Students would often have trouble with the product rule for exponents, and I told the professor to make a better tutorial for that specifically. So I think hopefully that's been done. I don't watch the lecture videos these days, but hopefully that's included and whatnot. But anyways, that was one concept that really held people back. They forgot this long lost relationship in algebra, lower level algebra, that is really required for this course. And I have a second monitor, so I'm kind of Googling it right now, but I'm going to pull it up real quick. And that's a really important concept. Product rule for exponents. I'll just drag this over.
Exponent rules,
Yeah.
Partial fraction expansion. We run into a lot of that in the second half of the course.
That's true.
They have a good handle on that.
Certain websites, I kind of like their aesthetics better. All right, well, here we go. Product rules. So this, let me zoom in so I can figure on your guys' screen. So this is the product rule for exponents. It's a algebra concept. It says that if you have a base to some exponent times the same base to some other exponent, those exponents add. And as you can imagine, since we're dealing with complex exponentials all the time, the complex exponential is E, so every term has a base E, and then you have some exponent is a complex number, j or I times some argument theta. Well, you can just basically add or subtract those all over one term, and that can be used to simplify problems. So understanding and using this rule is paramount to this course. By extension, the
same base.
Yeah.
Same
different base, but same exponent. You don't see this one so much in the course, but it's interesting that's here. I actually meant to highlight this. So this is the same thing as this, but with division, the quotient rule, is basically the same thing, but you subtract certain. So we see that all the time as well. Just as a quick reminder, this rule right here, this is, people often overlook this. If you have a negative exponent, like we do in Euler's identity for sines and cosines, or we see in Fourier coefficients and whatnot, you always have a positive j times theta and a negative j times theta. Well, whenever you have a base times a negative exponent, otherwise known as a decaying exponential, what that really means is that you have 1 over the base times that exponent. So it's the inverse. And this just goes to show you, as n gets large, you're really dividing by that whole number, which means that you're approaching 0. So I know that's a little basic, but it's important to understand these rules in algebra because it really helps simplify things. Another thing, let me see, the question was that things that we wish we understood better. Another thing that I find really important or useful is, why is my computer not working? There we go. Going back to the key concept sheet. Am I on the right one? I think it's week 2. Oh, this one right here. So the sampling property of delta functions and the sifting property of delta functions. Now, Dirac deltas are interesting little cheat codes to mathematics. I say they're cheat codes because they're not physically realizable. They're a cartoon of things that we can approximate in real life. So one interesting thing is the lab 2, where we do the convolution with the lady singing. We convolute it with an impulse response from 3 different environments, from the Grand Canyon and a church and Opera Hall or whatever. So those impulse responses are mathematically described using Dirac deltas, but in real life, they're approximations of Dirac deltas are things like a clap or a gunshot, because they, well, let me mention the definition of a Dirac delta. It is a structure or a curve such that the area under this curve equals 1, but the width of the curve is approaching 0, and thus the amplitude of this curve approaches infinity. Well, if I wanted to approximate something that's really skinny with a high amplitude, well, a clap approximates that. If you look at a Fourier or a spectrum analysis of a clap, it is a very thin, high amplitude curve. And so we use that in audio and signal analysis and stuff to approximate Dirac deltas. Now, anyways, back to what I was discussing was the sifting property and the sampling property. The sampling property says that if you have anything, this could be a system or a signal or a function, whatever. If you have a thing times a Dirac delta, the Dirac delta pulls out the thing at whatever the argument of the delta was. Well, yeah, this one is, the argument of the delta is, it procs at t equals 0. In other words, the Dirac delta is 0 everywhere except for where t equals 0, or where the argument returns 0. So I really should be paying attention to this one, because this allows us any arbitrary delta. What if I shifted my delta away from the origin? Well, t minus t naught equaling 0, then procs this Dirac delta to pull out the amplitude of this signal at that point. So that's what this statement is saying. Put another way, let's say I want to sample a continuous time signal with a inherently discrete time system, like a computer. I have a computer that's recording temperatures from a temperature sensor every second, let's say. At the first second, or at 0 seconds when I first turn on the system, I'm going to pull out the amplitude of the temperature sensor. Let's say it's, I don't know, 60 degrees. At the next second, it's 61 degrees. At the second after that, it's 62 degrees. So the computer is recording these discrete amplitudes of the temperature at that instant in time. Because a computer can't operate in continuous time. A computer is, ones and zeros, just discrete in time, using a clock signal. It operates on a clock. So that's what this statement says. Now the sifting property is almost the same thing, except that it's the convolution of a thing, a signal or a system or a function, convoluted with the Dirac delta. And what that says is that I'm going to, I don't want to use the word sample, but I'm going to sift or look at this signal at different points in time, I guess, and return that same signal. So that means, and then the time shifted Dirac delta, all that means is that I'm going to take the same signal and then just shift that entire signal to whatever the argument of the Dirac delta was. And that's what this says here. Now, why that's important? I just lost my train of thought. So in terms of like systems that we're familiar with in real life,
well, if you recognize it early, you can sort out some math that makes it a lot easier.
Yeah. Okay. So using like an audio engineer's standpoint or perspective, let's say I have a recording. Let's say I'm a sound engineer and I'm in a recording studio with some artist and they're singing and they want some funky beat in the background and they want some cowbell. You're going to be, as a sound engineer, you're recording these three separate things separately. There's a person singing and they have headphones on so they can hear the music and keep the human will keep on time that way. And then you record the cowbell separately using a different microphone, and you record the funky beat separately as well. Maybe it's a drummer or a guy playing a guitar or something. So when I build the song before publishing, I have to merge these three different recordings onto the same track, I guess. So let's say the beginning of the song is just singing, and then in the middle of the song it's just instrumentals, and the cowbell only happens a couple times in the song, maybe during the bridge or something. Well, if I take my recording for the singing, he's only singing at the beginning. So I'm gonna take the singing signal and sift it using the Dirac delta and return that signal centered around the origin. The cowbell only happens later in the song. So I'm gonna take a recording of a cowbell that starts at t=0 and goes on to a few seconds, however long your cowbell lasts for. But I want it to be later in the song. I want to shift this cowbell sound to later in the song. So I take the Dirac delta by, at a shifted argument and return the cowbell sound later down the track. And then same thing with the instrumentals. So I want that sound to appear later in the track. I'm going to shift it in time, not just a couple points of that signal, but the entire signal, the entire recording of the cowbell is going to be later in the song. That's what this shifting property allows us to do. So hopefully that gives a intuitive understanding of what shifting does. So back to what it means for us in the weeds of solving problems. Dirac deltas, or sampling and shifting properties, allow us to greatly simplify problems. Yeah, we'll see that a lot more in later in the course. I think we saw it a little bit in week 3 concepts. Jamie, do you have anything to add? Important concepts that you thought were really useful for midterm material? Or
for midterm? No, I mean, you're gonna have a shift problem, like a systems properties problem. Um, Stability and gets real tough to explain at this level. I mean, you'll get a more formalized definition of stability in week Laplace transform 6, I think. But the basic idea is it doesn't feedback on itself and blow up. Um,
That's a good point. I would like to talk about these LTI system properties real quick.
yeah.
So as Jamie mentioned, stability is important. I don't honestly remember a whole lot of stability questions on homeworks and exam problems and things like that throughout this course, but I took the course like two years ago or something like that. Anyways, from an engineering standpoint, though, stability is very important. If you have an unstable system, let's say we're talking about an amplifier, it's taking a small signal, you amplify it to become some big signal, maybe you apply that to an antenna or something, and you're trying to transmit it really far away. If you had an unstable system, that amplifier would literally overheat and burn up. So when you're doing the mathematics, before you actually build whatever you're designing, stability lets you know if it's practical, if it's if it's not, if it's going to be durable and reliable after continued use. The good analogy or example that I usually talk about is a microphone being too close to the speaker. So if a guy is talking on a microphone, giving a speech or something, and the speaker's like right behind them, if the speaker picks up the guy's voice before it even gets in if the microphone picks up the sound that's coming out of the speaker as if it was the person, microphones are tuned to only pick up the sounds that are a meter or foot away or so. But if the speaker's too close, then the microphone's going to be picking that stuff up too. That signal will then get amplified and then played out the speaker again at a louder, higher volume, and then you have a continuous loop where it just keeps going. The microphone picking up speaker sound, amplifying it, going up the speaker again at a higher rate, so on and so forth, ad infinitum, until you get that really loud screech, or until you burn out your amplifier. So you want to do that, and the way we solve that problem in real life is either design your amplifier to cut out, to filter out really high frequency, high volume signals, or just have the speaker step away from this. Have the talker, the person speaking at the audience, step away from the speaker, the one saying the audio, and that usually fixes that. Now,
while I'm unmuting the other computer.
Now for these other things, memoryless, invertible, causal. Causality is interesting and important. So if we want to build, so it's easy to think of a system that's discrete. We're talking about a computer being tied to a sensor of some kind. The computer is sampling the sensor at discrete intervals, like maybe once every second or once a day or once every 50 milliseconds, whatever the case. But we can also design systems that operate and function in continuous time and are not discrete in nature. So we're talking about a receiver, an analog receiver, taking a continuous time signal from maybe an antenna and doing some manipulation to it, such as AM demodulation, and then applying it to some other subsystem, like a speaker or whatever. Causality is really only important for your continuous time systems, because continuous time systems operate in this universe, and this universe is we can only march forward in time. We can't time travel, so we can't go back in time. We can't reference, or we can't go forward in time either. We can't reference data points from a temperature sensor that happened in the future, and we can only reference data points that were in the past, if we have some kind of recorder or buffer that's holding that data before it gets operated on by the rest of the system. So that's causality. Now, causality for discrete time systems is different. So we have the benefit of really large memory and really large storage devices like hard drives. And we can record an entire song, for example, or a lady singing like we did for the lab, and we can do anything we want with it, basically. The last part of the lab really illustrates, I hope people kind of notice, but it really illustrates, the last part of the lab is when you play the song backwards. That is an anti-causal system. You are taking the future samples of the lady singing and playing it at the beginning of your output, I guess. You're playing it backwards. That would be physically impossible with a continuous time signal or a continuous time system, because you would need a time machine to know what the lady's singing in the future and then play it, right now. But we can't do that. So, but anyways, in discrete time, it's really easy because you can just record the whole thing and then you could do whatever you want. You could, take all the even amplitudes and play them first, and then the odd amplitudes and play them second. You can do really weird things. You can invert the amplitudes. You can play it backwards like we did. You can slow it down, speed it up, all kinds of things. So that's why causality is important. Really limits you in the continuous time analog sense, but does not limit you so much in the discrete time computer. You guys have any more questions? Let me see if there's any other stuff in the other weeks that I found interesting or important. Oh, as another little teaser, earlier I mentioned aliasing, and I didn't describe what that is or what it's for or anything like that, but understanding how we're calculating the period, and right now I'm highlighting continuous time. The period for discrete time is a little different than the period for continuous time. And this, like being able to calculate this properly is really important for understanding and using the concepts for aliasing. Just as a little teaser. I won't describe aliasing here unless you guys specifically want me to.
So is everybody comfortable with RP now? How that works? I'm about to post my exam tips, but from that, be sure to take the practice RP now test. You can take it as many times as you need. It's just to get you the functionality of how RP now works and how you upload solutions, that kind of thing. It's not any actual questions on the content of the course. So it's just get you the mechanics. After you finish your test, you're going to have to scan your solutions and upload them. You will not have access to email at that time, so you need to be able to scan your stuff to a cloud-based storage device of some kind. I use Google Drive, and that because you can still access your file explorer when you upload the file. So anyways, take the practice test, practice that, uploading your solutions within the shell of the RP Now, so you don't have any problems and they don't see an email or a text or a message on Piazza 11 o'clock and the exam's almost over that you're having problems. Be prepared for it, I guess. So that's for the mechanics of the test. To say that, and those property sheets are available you'll have to switch because you can only have one screen up, so it's kind of frustrating where you'll have to swap between your property sheets and the test. But you should be able to do that. It's just not as convenient as having an extra monitor and having it up there, or being able to print it out and take it with you.
Does everybody understand complex complex numbers and how you like get phase and magnitudes and stuff?
Mark Penny says, I use Rocketbook to take notes and do homework. It also allows me to take pics in the phone, upload to OneDrive. Could we use something like this?
Yes.
What's Rocketbook?
Oh, I don't know about Rocket, but I was thinking of OneDrive. You could, because OneDrive is cloud-based storage, and you can, have it run on your computer with with the file explorer, just like Google Drive.
Yeah, I was just making sure it's not like some like a tablet. You write down directly to a tablet, that kind of thing.
Yeah, Rocketbook you're probably not going to be able to use. You're going to have to take the exam on paper and then scan it.
Yeah.
Peter says, could you run over that phase and magnitude stuff again for complex numbers? Absolutely. Yep. And this is important for almost every class in engineering.
All the time.
Yeah, all the time. And very important for signals and systems too. If you take that pathway course, I definitely see it in like 60% of my classes, if not more. I'm just randomly throwing a number out there, 60%, probably like 80 or 90%. Anyways, okay. So we have these things called the complex numbers. We're familiar with algebra describing them in rectangular form, a plus jb. Now, just forest for the trees, complex numbers are a way for us to describe a two-dimensional system using only one dimension. That's the whole reason why we use it in mathematics and sciences and stuff. Being able to compress a three-dimensional representation of something onto two dimensions, which we do all the time as humans, or like living in 3D space. We have two-dimensional monitors, two-dimensional pieces of paper, two-dimensional blah, 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 and we always describe three-dimensional things on those two-dimensional things. A hologram is a compression of three-dimensional space onto two dimensions. Anyways, the way mathematically what you do, or to do that, you need complex numbers. So just to say it again, complex numbers are a way of compressing a higher dimensional object onto into a lower dimension. So the dimension that we're compressing to is the real axis, the real number axis. And then the imaginary axis is, well, it's imaginary. It doesn't exist, but it allows us to do things. Okay, so rectangular form, you have a real part plus or minus a imaginary part. So when I say the real part, I mean A. When I say the imaginary part, I mean B. The J is just a label that says this is the imaginary part. So a lot of times when you're taking the magnitude of something, such as down here, any of these, taking the magnitude, V of O is the magnitude of this complex number. We're taking just the real part squared plus just the imaginary part. There's no J in here. You don't square the J. J squared is -1. We don't have a -1 here. We remain positive. So that's something to keep in mind when you're doing the math, when you're writing it down on paper. We're taking just the real part and just the imaginary part, squaring them, adding them, and then taking the square root of. So you'll see this in Signals and Systems 2, if you take that class, and a bunch of other classes, where let's say you have a series of complex numbers. Let's say I have A plus JB plus C plus JD plus E plus JF, so on and so forth. Or like I have a quotient of complex numbers. Some complex number divided by some other complex number. You're going to be factoring and distributing such that you add them all up, so that you have something just over. You have just one expression, I guess, in the numerator and one expression in the denominator, and that allows you to basically have an expression of magnitude divided by the expression of some other magnitude. I'm getting a little deep, I guess.
Yeah. Vector.
What's up?
The unit vector of a complex. I'm sorry, I got lost.
Well, I do have something to show what I'm talking about. I have no idea what week to go to. Let's guess around. Bodhi plot. Here we are. So when we're later in the course, or not in this course, but in other courses, when you plot Bodhi plots, you do that on circuits 2, signals and systems 2, analog and digital circuits, EEE 304, a bunch of other ones. A bit better, prettier one. This kind of shows it right here. If I had some system and I have a bunch of series coefficients at the top and a bunch of series coefficients at the bottom, we call these zeros and poles, by the way. Anything in the numerator is a zero. Anything in the denominator is a pole. That allows us to see the behavior, the transfer characteristic of this system in a Bodhi plot. Well, when I take the magnitude, I'm gonna do everything I can algebraically to combine the entire numerator into basically one term, an a plus jb, and then I can take the amplitude of that, square root of a squared plus b squared, and then I can do the same thing with the bottom. Do everything that we can algebraically to combine these terms into a single term, a plus jb, or in this case, d plus jd. You do the same thing. D squared plus E squared, or what is, sorry, C squared plus D squared, square root of that. And then that gives you the amplitude of the numerator over the amplitude of the denominator, and then whatever that number comes out to be is your, or function, if we're talking about function, becomes your your absolute value of this complex system. I might be a little deep in the weeds now, but okay, so that's what these are describing, the amplitudes. Now, on a graphing calculator, which you are allowed to have in your during your exam, a graphing calculator. I wish I could show it, but if you have a TI 83 plus, for example, and you start writing out a function, like let's say you're in the graphing plot, and you click the little Y button to put in your function. To be able to plot the magnitude, all you would do is hit the math key, and then scroll over to CPX, which is complex numbers, and then you scroll down to absolute value of, which is number 5. Then you put your entire function inside that parenthesis for the absolute value, and then close your parenthesis and then hit go, and it will plot it in real coordinates. If you want to plot the phase curve of a function, you do the exact same thing. You hit the math button, go over to CPX for complex numbers, and instead of hitting 5 for absolute value, you would then just hit 4 for angle of. And then you close the parenthesis and then hit plot, and it will give you a cool little curve for the phase. To do it manually on paper, I just kind of described the amplitude or the magnitude, but the phase, all you're doing to get the phase is you have to convert from rectangular form into polar form. Now polar form, polar form and exponential form are the same thing. This is just a shorthand notation that we use in electrical engineering, and this is what you're actually doing mathematically. You notice we have a complex exponential, and that's why Euler's infinity comes into play a lot, and we can do differentials on these a lot easier because complex, the derivative of an exponential is just the argument of the exponential times the exponential itself. But to get the angle of, you're just taking the argument of the exponent, obviously without the j. Anyway, so that's basically just by inspection. You just, whatever is the argument of the complex exponential is your angle. But if you have something in rectangular form where we have a plus jb, you have to do a little bit of legwork to get the angle. Now the definition of the angle to get theta from the rectangular form is just the inverse tangent of b divided by a. Now notice this is not including the j. The j, as I mentioned before, is just a label to say that the number after it is the imaginary part. So in other words, to get the angle, you take the inverse tan of the imaginary part divided by the real part. That's what that says there. Now, if you have a function, rather than just straight up numbers, you're going to be doing the same thing. You're going to be taking the inverse tan of the function that describes the imaginary part, divided by the function that describes the real part. And then you can't, that's harder to actually get a real curve by hand, but a graphing calculator can do it easy if you just use that angle button that I described. You go to math, over to complex numbers, scroll down to angle of. Input your function divided by the function of the imaginary part divided by the function of the real part, close your parentheses, and then hit graph, and you should get a nice real valued curve. So
yeah, I think you're only required to do that for the homework. I don't think.
Yeah, you're not going to have to worry about that so much for the exam. So Peter, I hope that kind of summarizes the complex numbers for you. If not, I can go a little bit more. Just let me know.
Well, I tested in this class. I'm confident I'll have to do it in circuits 1 and 2.
So I got to catch up on this fact right over here. So Jamie, you wrote.
We were talking about Rocketbook.
Right.
And I misspelled your name, among other things.
Oh, no.
It's horrible.
Oh, for complex numbers, okay, so this document is 4 pages long, so it's not too long, but to really summarize the gist of the really important stuff for complex numbers, I wanted to say this earlier. If you are concerned with the magnitude of your complex number and you want to add magnitudes, it's best to keep your expression in rectangular form to do that. Wait, I'm sorry. Let me back up.
When you add and subtract, you want to be in rectangular. When you divide and multiply, you want to be in polar.
Yeah, that summarizes. That's what I want to say. Well, to take that statement a step further, though, when you're worried about the phase of something, the angle of something, angles add and subtract. If you have theta, you just add and subtract them. The magnitudes, though, the table is.
Add to us conversion performs heavily.
Actually, this is really important.
Yeah.
For the class that I'm in right now. The magnitude times the magnitude conjugate equals the square of the magnitude. That's used in quantum mechanics all the time.
Yeah, Mark, I just had to do homework for my 470 class. The first problem took me 4 pages because I was constantly converting between polar and rectangular just to add and multiply what I needed to get an equivalent evidence circuit.
Yeah.
So it never goes away.
The only time you have to do it by hand, though, is when you have functions. When you have functions that you want to add or subtract the magnitudes or add or subtract the angles. Sorry. If you have less pure numbers, though, a graphing calculator can do that in a breeze. So again, if you're on a TI-83 Plus, you just hit the math button, scroll over to CPX, and you would just hit absolute value of for magnitude or angle of for phase.
Also,
if you want to convert from rectangular to polar, you have a couple more functions that in the same menu option. So option 6 has a little right arrow and it says rectangular or RECT, rect for rectangular. If you have a answer in your graphing calculator in polar form and you want it in rectangular form, you just use this function here. And then vice versa. Option 7 or item 7 is converting from rectangular to polar. Now another thing you can do also without having to use the math button is you can just set your graphing calculator to a mode that always displays answers in rectangular form or always displays answers in polar form. And what you do to do that is you would hit the mode button, which is at the top next to the second button, and then the third option, the second to last option at the bottom, your graphing calculator, when you get out of the package, defaults to real. You would want to scroll over to A plus BI for rectangular or R e to the theta j or I for polar form. And that way, whenever you input an expression, if you want it to always default to give you rectangular or polar, you would just flip these two options in the mode. And that can be sometimes quicker than using the math key to use the functions. So I do that all the time in homework problems and exams and stuff. So I haven't encountered a class yet that I couldn't use my TI-83 Plus. Well, for junior and senior level classes at least.
MATLAB also does the same function, and I like it because you can see the old values and stuff like that.
Yeah. MATLAB's great because you can do it on an entire array or matrix of complex numbers.
It'd be nice if I could figure out how to take it out of radians mode and put it in degrees mode, but I don't think that's an option.
Well, you would just write another line of code that converts it for you manually.
Yeah.
Yeah, keep that in mind, actually. That's a good point. For lots of classes, I don't know if it comes up so much in this class, but be aware that a lot of expressions are native, like mathematically speaking, native I'm sorry, I just lost my train of thought. Oh, in radian. Yeah, a lot of stuff is given in radians. Like in physics classes, whenever you have an expression, it's almost always going to give out an answer in radians, and you have to remember to convert it to degrees.
Yeah.
Us humans like degrees because we were born that way, or like we were raised that way. But natively, mathematically, radians is the natural unit for angle. So that comes up a lot in signals and systems too. The professor wants you to display your answer in degrees. We speak in terms of degrees, but what you input into your calculator is in radians.
Yep.
Are we limited to a specific calculator during the midterm?
I don't think so in this one.
I don't think so either. Let me go to the syllabus and look.
I know some classes limit you, like can't have a TI-89. I have an Inspire and an 83 Plus. I think I've been able to use my Inspire on everything but like one class, which was IEEE 380, the statistics class. They wouldn't let us use the Inspire, but we could use the 89, which was weird. Because the 89 has more functionality. But I think for engineering, they don't give they don't care what you use.
Yeah. Reading the syllabus, it says a handheld or computer built-in calculator. So that's any calculator of any kind. The only time I've seen at ASU or in general that the professor cared about what kind of calculator had was just in the math classes. The calculator does a lot of work for you, and in the math classes you have to show that you know how to do the work, not the calculator. But in all the regular engineering classes, the tedium of getting through a math problem is not the important thing that you're supposed to be focused on. The thing you should be focused on in the engineering classes is how a system behaves, or what it does, what it's useful for, that kind of stuff. Not the math, Yeah, the math classes, the math professors in the math department at ASU, they, in general, they do not like calculators that can operate symbolically. Only the ones that can operate numerically.
Yeah. And to be fair, their point of their class is to teach the tedium of the math.
Yeah.
not to. We assume you know that tedium and can actually apply it to something.
Yeah. I'm not gonna lie, I don't ever solve derivatives and integrals by hand anymore.
No.
Why would I? Actually, I'll show you guys since you guys are here. So I already have a browser over there. Let me just use that one. This browser here. So if you're not aware, there's a couple really awesome websites. Here's the Online Derivative Calculator and Online Integral Calculator. A lot of people use Wolfram Alpha and Simulab or SimLab, whatever it's called. I really don't like those ones because their user interface sucks, and they're confusing, and they, I don't know. This website, derivative-calculator.net, and then you can just click this button to get the integral calculator, or remember, integral-calculator.com. And these are really awesome because you can input an expression. You can use any variables you want. You have these options over here where you can differentiate with respect to a certain variable. So like we use X a lot in mathematics. We use T a lot in signals and systems. In Calc 3 and stuff, you might use R for the radial vector or physics or whatever. You could use any of these, differentiate with respect to. Otherwise, D of D, T, D of D, Z, whatever you want. You can tell it how many times you want to take the derivative of. So first and second derivatives are really common. You can simplify roots. You can use the complex domain. You can even have it calculate numerically only and not worry about symbolic calculation. And that option is right. I guess it's not here. I thought it was here. Anyways, when I hit go, it calculates, and then it gives me what I wrote for my function, and here's the answer. You can then click and this is all free, by the way. You don't have to pay a subscription like you would with the Wolfram Alpha or any of those other ones. I can show steps, and this would show me how it calculated that derivative symbolically, and I can scroll down, and this gives me, this is only for the integrals, but it gives me a numeric. Yeah, let me hop over to the integral calculator. The integral calculator gives you both a symbolically generated answer and a numerically generated answer. And if they agree, then you have high confidence that the calculator did it right. So on the integral calculator, you can also show steps for free using different, this is using use substitution here, and then it does integration by parts here, twice in a row, so on and so forth, blah, blah, blah. Scroll down, you get to the answer. Here's the numerically generated one. And then on here, you get the plots, the graphs. So the red one, you can see the labels up here. Maybe not. Oh, yeah, you can. So the manually computed one is we're calling F star of X. And the numerically generated one, we're calling just F of X. So you can just see the plots here. You can see that both curves, both solutions agree with each other because it's the same curve on this plot. I can zoom out, I can shift around if you want to see different parts of the graph. And see, ooh, this is a very interesting curve. And then you can actually input some different values and get a number, look at it in, in a table. Yeah, this grapher or solver is awesome. And then with the integral calculator, I didn't show the options, but the options are a little bit more than the derivative calculator. You can actually calculate both an indefinite integral and a definite integral. You can put in values here. You can even put infinite and negative infinity and infinity and get an indefinite integral. And then here's the option where you can integrate numerically only, because there's a lot of, and this is really common in signals and systems too, EEE 304, right? Where whatever methodology this calculator is using will not like, I don't know how to describe it in a way you guys would just easily understand right now. But anyways, well, needless to say, the option's here if you need it. In the future, you will need this.
I don't think you can use that on tests, but yeah.
No, you can't use this on tests. But it's great for homework. It's great for understanding problems, and it's great for just getting through something really quickly. Not have to do integrals by hand or derivatives by hand.
Cool.
Yeah.
Man. I almost posted my test taking tips to my 488 Piazza display. And I'm like, that's weird, but thanks. We have no tests in this class.
What? I would love to take a class where there's no tests.
Wow. I mean, I guess there's no test. It's you got to build something, but
yeah.
Some formatting. I think that's something more like the humanities. Like my wife, she's going for her social work master's. She doesn't have any tests. She's got papers.
Yeah.
Really have a test.
No problem, Peter. I just saw your message. Saying thank you. Hopefully, help you out. Our pre-recorded video is better for how to actually get through problems.
Yeah. I knew this stuff better then.
Oh, sweet. Okay, it's just us, Jamie.
Cool.
We're free.
Oh, we'll stop recording.